Good evening, everyone sitting. My name is Joshua, and I will be presenting on the biosorption of Levervix Brilliant Blue dye using dried Saccharomyces cerevisiae. We'll be looking at the kinetic study, the equilibrium, and the thermodynamic assessment. Saccharomyces cerevisiae is also known as yeast. Biosorption is a physicochemical process that is based on different processes like absorption itself, absorption, ion exchange, surface complexation, and precipitation. This process is highly important in the environment and conventional biotreatment processes. Biosorption is used for the recovery of organic substances like dye, antibiotic, phenolic compounds, and also inorganic compounds like heavy metals, for instance copper and all of that. The volume and composition of dye that is entering the water body every year is so high, and some of these dye contents are poisonous, some of them are mutagenic, some of them are carcinogenous, and it actually affects the processes going on in the water body as well. It affects the growth of some living organism in water body. That means there is a need for us to find a solution to this problem. Not only finding a solution, but finding a solution that will somehow not create a secondary solution problem for us. Saccharomyces cerevisiae is very easy to grow in the lab, and it can also be obtained from the industry, and it is seen as an organism that is not problematic to us and to the environment, and that is the reason why we choose this material. Yeast, as we all know, can be grown cheaply, because in science we look at the economic aspect of whatever we are doing. We want to find a cheap solution to any problem that is ongoing. This research is meant to remove this particular dye using Saccharomyces cerevisiae from aqueous solution. Specifically, we are looking at the biosorption capacity of this material. We are looking at the effects of operational parameters such as pH, initial dye concentration, time, biosorbent dosage, and also we want to see the thermodynamic behavior, the kinetic behavior, and the isotherm behavior of this process. As I said the other time, the material is available, it is easy to prepare, it is cheap compared to our conventional method that we all know, which is activated carbon, and it is environmental safe. The dye, we are at the materials and method. The dye is gotten from our lab, and also the biosorbent, which is yeast, is purchased commercially. We grew the biosorbent in the lab with glucose and water. It is easy to grow. And also the sodium androxide and hydrochloric acid that we used to adjust the pH was gotten from our lab. All the various concentrations were set up by diluting the prepared stock solution, which we did 1 gram per liter. Now, we find out the maximum wavelength of this particular dye, as we all know that each dye has the maximum wavelength. We did it with the use of UV visible spectrophotometer, and the calibration curve we also made to be able to determine the...
I think we can skip this material method. Let's go to the results. Very good.
Okay, thank you. In the results, we find out that the removal efficiency increases as the pH of the solution decreases. we see that at acidic pH, we got good results. The best result was gotten, close to 100% was gotten from pH 3. This same result has been reported before by Eckert et al. And Mahmoud et al. This observation could be ascribed to the electrostatic attraction between the negatively charged dye molecules and positively charged cell of Saccharomyces cerevisiae. This is the result showing the effect of biosorbent dosage on the process. We see that too much dosage is not too good. Likewise, too low dosage is not too good. But we see that as the dosage is increasing, we are achieving good efficiency in the process. The same result was observed when Saccharomyces cerevisiae and this other organism was used to absorb reactive grain dye. The result of this investigation could be attributed to the interaction between the dye ion and the binding site of the biosorbent. This is showing us the results of the effect of initial dye concentration on the process. We see that from 25 to 250 milligram per liter, we are achieving good results. As the initial dye concentration was increasing, we see that we are achieving efficiency because the surface of the yeast we use were still enough to catch up much dye into the cell. The result that is very important to us in this study is the isotherm, the kinetic, and the thermodynamic assessment. Because, for instance, the isotherm makes us to understand what is actually happening in the process, the mechanism of the process. So, we tested various models like Freundlich, Langmuir model to see which one fits best to what we have done. And the results show us that Langmuir model fits best to the process because the coefficient rate were near to 1, more than 0.9, which shows that it's actually a good experimental data for us, and it shows that the yeast is also good for the dye, and it also implies that mononuclear absorption of the dye or homogeneous surface of the biosorbent. The same result was obtained by Eckert et al. In 2012. And the reason why we use DR model was to study the energy and to know the likelihood of whether it is physical absorption or chemical absorption, because there are standard data that for instance, if E value is less than 8, we can say it is physical absorption, which we have in this particular experiment. For the kinetic study, we look at first order kinetic, we look at second order kinetics, and Weber-Morris. Weber-Morris is very important to us because we want to see the rate that is the limiting step in the process. And we could see that from the table, the C is not equal to 0, which indicate that both intraparticle diffusion and boundary layer influence the biosorption. It also revealed that intraparticle diffusion model was not the only rate controlling step. This is the table of kinetics. And for the thermodynamic study, which is the last study, the value of delta H and delta G are negative, which shows that the biosorption is feasible and spontaneous. The positive values of delta H also indicate enhanced randomness at the solid-liquid interface amid the absorption procedure. And the delta G calculated for Saccharomyces cerevisiae at different temperature are between 0 and minus 20, which indicates that the process is physical. The study implies that in a place like this, we can use cheap materials instead of expensive activated carbon to treat dye wastewater. Also, the high temperature that we use in this study from 30 to 45 degrees means that the study is possible in Cyprus like this, and it can be transferred to industrial practice, large scale practice, even in the summertime. And in conclusion, absorption efficiency reduces as the solution pH increases, meaning the maximum bioabsorption of the dye took place at acidic pH. There was no significant influence of temperature on the bioabsorption process. The thermodynamics analysis of the experimental data suggested the process was feasible and spontaneous. And we also saw that the process was physical absorption. It may be concluded that cleanup of environmental pollutant using natural resources such as yeast, which is low cost and effective without posing threats to secondary pollutants, is very possible. These are my selected references. Thank you for listening.